And what I want to point out is that this map, the Lorenz map itself, is a chaotic dynamical system, right? So it's called a discrete time dynamical system because the time is discrete, 1, 2, 3, other than continuous. And this is nice because it allows us to visualize the distribution in 1 dimension as opposed to 3 dimensions. So Lorenz actually studied this map a lot, and although this map is nice, it does not have a closed form. And to further make the study easier, Lorenz also simplified further this map into a map that goes straight up and straight down, right? That's called the tent map. This map not only is easier to study in 1 dimension, it is also still chaotic, right? A small perturbation will always lead to twice the amount of perturbation in the next iteration, and it has a closed form. So we have simplified things to its extreme. This tent map has a physical solution that is distributed uniformly in the interval from 0 to 2, right? So the density is 0.5. And it's actually pretty relatively easy to prove that mathematically. What I want to show you is that how does, for example, periodic non-physical solutions would arise for this particular map. And using this particular map, we can now start to study more difficult to find type of non-physical solutions that turns out to be closely linked to shadowing. Okay, so first of all, on the tent map, because of the straight line, you can see that if you started from 1, right, you're going to map to 0. If you start from 2, you're going to map to 0. If you start from 0.5, you're going to map to 1 and then back to 0. So if you start from any fractional number with the denominator being a power of 2, you are ultimately going to be mapped to 0, right? That's just a fact due to the linearity of the map and the slope of 2. In addition, if you started from any rational number, let's say 1/3, you're going to map to 2/3 and then map back to 2/3. So you get periodic solutions actually starting from any rational numbers. And what's interesting is that if you can write down the formula of this map, and if you can represent every number, right, in the solution into binary decimal form, right? This is the binary decimal representation of the xi. It turns out you can write the map in symbolic form, right? So basically the ith digit of the k plus 1th solution, right? The next solution is equal to the 0th digit of the last step, or the integer component of the last step, XOR with the I plus 1th digit of the last step solution. Now, what is significant on this is that it allows us to play around the solution in a very interesting way. For example, you can represent all the periodic non-physical solutions in terms of binary decimal digits, where the digits would repeat itself, right? If the digits repeat themselves, as the digits shifts, I mean, this is really a shifting and inverting operator. As it shifts and inverts, they are going to repeat themselves. You can also represent all the physical solutions that way. If you have a physical solution, all the binary digits are going to be IID. They're going to be independent and identically distributed. Okay, and it turns out we can construct another set of quasi-physical solutions, right? I'm going to refer you to this reference for all kinds of interesting numerical artifacts that you can observe on these systems.